To calculate the acceleration, we're going to isolate the whole system. Okay, so there's the whole system. The weight force is the total mass times 9.81. The total mass is 15. So this is 147.15. Then there's a, well, I'll put the 20 down. There's a 20 Newton force there. And then there's a pushing force from the ground that's perpendicular to the surface. So it's not straight up, it's at an angle. Okay, and I'll call that N total. As far as the weight force, we're using this coordinate system. The weight is like that. This angle is 15 degrees. So the angle, yes?
Is it 10 and 15 kilograms or 10 and 5 kilograms?
10 and 5.
Okay.
Yep. So the angle that you're going to use with cosine and sine going all the way from the positive x-axis is 90, 180, 270 plus 15. So this is 285. And so Newton's second law says 147.15 times the cosine of 285. 147.15 times the sine of 285. Plus 20, negative 20, sorry, that's in the negative x direction. Plus 0 N total. Is equal to the mass, 15, times the acceleration. Is this free to move along the x or y axis? X, so I'm going to write this as A0. And so the x equation here says 38.09 minus 20 is equal to 15a. So 18.09 is equal to 15a. So a is equal to 1.21. Now to get the vector, you can just plug it into this acceleration vector, and it tells us that the total acceleration vector is 1.210. So is that up or down the ramp? Down the ramp, yep. So even though there's that 20 Newton force pushing it up the ramp, that's not enough to overcome the weight. So it still is accelerating down the ramp. Can we tell whether this is speeding up or slowing down? In order to tell whether it's speeding up or slowing down, I would have to tell you which way its velocity was at this instant, and I didn't. I have to if there's friction. I could if there's no friction, but it doesn't affect the calculation, so usually I don't. So we don't know. This acceleration is true whether it's, no matter which way its velocity is moving at that instant. Okay, so now the second step is you're going to isolate one of these two carts to to calculate the reaction force between them. It turns out you could isolate either one of these. Probably the more direct way to go would be to isolate the 10 kilogram one, and then the force that you calculate is the force we're looking for, the one on the 10. But if you feel pretty good about that stuff and you want to try out thinking about Newton's third law, try isolating the 5 kilogram cart and see if you can go from there to figuring out the force vector on the 10 by the 5. So, okay, go ahead and try to calculate that force on the 10 kilogram by the 5 kilogram. Ways to do this, I'm going to do them both. The more direct way would just be to isolate the 10 kilogram. Okay, so this, there's a weight force down of 98.1. There's a pushing force from the incline. I'll call that N10. And then there's the reaction force. This is the force on the 10 by the 5. This is what we're looking for. So Newton's second law says 98.1, not 981. So 98.1 times the cosine of 285, 98.1 times the sine of 285, plus 0 and 10. That r is acting in the negative x direction, so plus negative r, 0, is equal to the mass times the acceleration vector, which we just figured out. And so now the x equation says 25.39 minus r is equal to 10 times, this is actually 1.206, so 12.06. And so r is equal to 13.33. This is in newtons. Well, now you could think of it as having this magnitude pointing in the direction of the arrow, or you could, to come up with components, you could plug it into this. This right here is the force on the 10 by the 5. And so the force on the 10 by the 5 is negative 13.330. Okay? But I could have also isolated the 5. Okay, so let's do that. So we have the 5 kilogram. The weight is 49.05. There's a 20 Newton force this way. There's a normal force I'll call N5. And then there's a pushing force from the from the 10. So I'll call that R. Newton's second law says 49.05 times the cosine of 285. 49.05 times the sine of 285. Minus 20, 0. Plus 0 in 5. Plus R0 is equal to the mass times the acceleration so the X equation says 12.70 minus 20 plus R is equal to 6.03. So that is 7.3, so 13.33, I think, is equal to R. Well, I know that has to be the right answer because we have to get the same thing we did using the other approach. But now you have to think a little bit about the directions, okay? So what we have here, this is the force on the 5 by the 10. And that's not what we're asked for in this problem. We're asked for on the 10 by the 5, okay? But remember that Newton's third law always says the force on one thing by the other is equal to -1 times, in this case, the force on the 5 by the 10. If you're talking about the same contact force, you're just switching which one it's acted on and switching which one it's acted by, then all you have to do is switch that vector. The force on the 5 by the 10 is equal to 13.330. And so that's equal to the force on the 10 by the 5 is the negative of this, which is negative 13.330. And it matches the answer we got doing it the other way. Okay? Anybody have any questions about that? Okay, so now let's do one where we have a block. Let's say this is 1 kilogram. And it's connected to a hanging mass of 2 kilograms. And let's say the coefficient of friction, I'll put it over here, is 0.4. And let's say that at this instant, the motion of the 1 kilogram block is to the left, okay? So what you can imagine happening is that something gave this a really big shove, and before it could before it could slow all the way down and stop from the friction, we decided to take this measurement while the thing was still sliding to the left. Okay. All right, so first of all, is there any reason on this to use a rotated coordinate system anywhere? No. If you use the rule for rolling and sliding, you just get the normal coordinate system back for this. And then the other question is, do these have the same acceleration or different acceleration? No. Different. And so we approach this differently. In this case, instead of isolating the whole thing at once, we isolate, one at a time. So let's start by isolating the 1 kilogram and figure out what you can from that. And like before, I'm going to give you a few minutes to work on that, and then I'll go through it. So see if you can come up with the equations for Newton's laws, for Newton's second law, for the 1 kilogram box. So I'm going to start out by isolating the 1 kilogram. You have a weight down of 9.81. A normal force, I'll call N. A cable force T. And then you have a friction force that's opposite the direction of motion. And the magnitude of that is 0.4 times this normal force. And so Newton's second law says T0 plus 0.4 times N, 0, plus 0N, plus the weight, 0, negative 9.81, is equal to the mass times the acceleration. Does this move along X or along Y? X. So I'll write this as A0. Well, the Y equation says N minus 9.81 is equal to 0. So you can solve that for N. And now I'm going to plug that into the X equation. So we have T plus 0.4 times this value that we now know for N is equal to 1A. And so we can write this as T is equal to A minus 3.924. Okay, now isolate the other one and see if you can come up with an expression for the acceleration. I guess I didn't say which one. Let's calculate the acceleration vector of the 2 kilogram. Okay, so free body diagram of the 2 kilogram. We have 19.62 down. The cable force up. Newton's second law says 0T plus 0, negative 19.62 is equal to the mass times the acceleration. Okay, so now we have to think about the acceleration. If we move the 1 kilogram, like we have this A in the X direction, right? So if we move the 1 kilogram an inch in the positive X direction, where does the 2 kilogram move? down, and it moves an inch. It doesn't have any funny relationship. So this is just going to be 0, -a. Does anyone have any questions about that? That's definitely the trickiest little thing about these kind of problems. Then the y equation says t minus 19.62 is equal to -2a. That's our second equation. And so now I can solve this system of boxed equations together. I'm going to just use substitution. I'm going to substitute the stuff on the right side of that top equation in for t. So we have a minus 3.924 minus 19.62 is equal to -2a. So a, I guess 3a if we get them all over to the left. And you get that 3a is equal to 23.54. So a is equal to 7.848. Okay, now we want to use that to express the acceleration vector of the hanging mass. This is the acceleration vector of the hanging mass. And so the acceleration of that 2 kilogram object is 0, -7.848. Or in other words, downwards with a magnitude of 7.848. Any questions about that? So is this system speeding up or slowing down? Slowing down, the velocity is to the left. The acceleration is, well, you know, the velocity is to the left and up. This time we got the acceleration of the 2 kilogram down. They're opposite directions, so it's slowing down. Okay, let's do one more. So let's say we have a 20-degree angle on that side, a 30-degree angle on this side. And let's say we have a block on this side that's 1 kilogram. And a cart on this side that's 2 kilograms. What's the acceleration vector of the 2 kilogram cart? And let's say that the coefficient of friction is 0.1. All right. Do these two have the same acceleration or different accelerations? Different. And then is there any reason to use a rotated coordinate system? And what do you think you do? There's actually reason to use rotated coordinate systems for both of these two. What do you think you do in that case? Any ideas? Well, just like in this example, remember, we didn't have to use a rotated coordinate system for the 1 kilogram. But if that was at an angle, we've seen it before where you use a rotated coordinate system for one and then a regular coordinate system for the other. So in this case, we're just going to use the preferred coordinate system for each of these two things. And it's going to work out just fine. You know, we're just going to come up with equations that are true from both of them, and then you can use them together. So we're going to use this coordinate system for the 2 kilogram, this coordinate system for the 1 kilogram, okay, so let's start with the 2 kilogram. Take a couple minutes and see if you can work your way through Newton's second law to come up with an equation there. So now, free body diagram of the 1 kilogram. There's a weight force of 9.81. There's a normal force, I'll call that N1. The velocity is to the right and down, so the friction force is up and to the left, and that's coefficient times the normal force. And then the cable force is the same as it was on the last body, T. This time our coordinate system is like this. And so what's the angle that I'm going to use with cosine and sine for this weight force? This is 20 degrees on this side. So 290, yep. Anybody have any questions about that angle? Okay, so Newton's second law says 9.81 times cosine of 290, 9.81 times the sine of 290, plus 0 n1 plus negative 0.1 n1 0 plus negative t 0, and all that is equal to the mass times the acceleration. So now we have to think about the acceleration direction. If you move the 2 kilogram mass an inch in its positive x direction, where does the 1 kilogram go? An inch in its positive x direction. Okay, so even though these accelerations aren't the same, they're expressed the same in their own coordinate systems, okay? But you always have to think about the geometrical relationships to get that. So this is going to be A0. The y equation says negative 9.22 plus n1 is equal to 0. So n1 is equal to 9.22. And now plug that into the x equation. And it says 3.36 minus 0.1 times 9.22 minus t is equal to a. And so that says 2.44 minus t is equal to a. So now I'm going to substitute this first boxed equation into the second one for t. So we have 2.44 minus, the expression for t is 2a plus 9.81. And all that's equal to a. So 2.44 minus 9.81 is equal to 3a. And so a is negative 7.37. Okay, we want the acceleration of the 2 kilogram. Well, I guess either way we'd express this the same. So we're going to substitute the a we got into just the vector a0. So the acceleration of the 2 kilogram is negative 7.370. Or in other words, down the ramp at 7.37 meters per second squared. So is this speeding up or slowing down? We got an acceleration of the, like each of these sliding to the left. The velocity is to the right, so this system is slowing down. Any questions about that? Yes?
What did you do with the 3A?
It has it.
Were you supposed to divide that by 3A?
You're right, I did not. Thank you. 2.46. Okay. All right, let's do the quiz.